Cool. Okay. Well, yeah, I guess it's like a bridge theme today. So I'm going to be talking about a lot of the same core concepts that Shane was talking about, but a little bit different. I'm going to kind of go through what it means to build a natively cross-chain application instead of just a standalone standard Web3 application. Okay, so first I want to go through a little bit of background. I'll go through this pretty quickly since we did just do a talk about bridges, and just kind of go through the different types and their trade-offs. So first is a natively verified bridge, and basically these are like your light client relays, and what this means is the domain's underlying validators, so like the stakers in a POS chain are validating that this transfer has happened. Roll-up AMBs are a special type of natively verified bridges, but it means that both chains are using their underlying security set to validate that that state transition has happened. You also have externally verified bridges. These are also known as like multi-sig bridges. Basically, what this means is that you have a group of bridge validators who may be incentivized through staking and slashing, or they, help run the project for whatever reason, but they are the ones who are validating deposits and withdrawals into and out of this bridge. Those are great because they're pretty quick to use. The downside is like your security gets reduced to the security of the bridge instead of being much more secure like the previous natively verified bridges, but natively verified bridges are really difficult to build and have to be unique for each execution environment. The last one is locally verified. These are like your atomic swaps. So basically you move funds from chain A to chain B to, okay, you trade me your funds on chain B and I'll give you mine on chain A. You basically have some two-step process where you put up your funds and you lock them in, and then you have some type of unlock condition where both parties can safely withdraw their funds once they've proved that they've been deposited successfully. But basically, it's just reducing this big problem into a problem with two people. This is great because you're not introducing very many extra security assumptions. You can validate everything yourself. The downside is it's not really. Oh, and you can take this to all different domains. Like really all you need is a signature. The problem is you can't really do too much else because you just have reduced blockchain's great composability, but you've reduced it to a two-party problem. Cool, so then there's also optimistically verified bridges. And what this pretty much works like any other optimistic system. Basically you have some record of state transitions, and that is signed by a staked updater. This updater broadcasts, or not state transitions, sorry, messages. This updater broadcasts all the messages, and you have a period of time where anybody can submit a fraud proof to prove that the broadcasted messages were invalid, and then watchers can disconnect your app so you're not processing any invalid messages. But after that period has elapsed, if there were no fraud, or if there was no fraud proof, then you can assume that the message is valid and keep moving. So these are great because they are kind of the best of both worlds. They do obviously introduce a security assumption, and that's like a liveness assumption of the watcher. But that's a pretty okay trade-off because it's a reasonable assumption, and you're able to take this to a bunch of different domains, and you're able to pass generalized data around. So you can do kind of more exotic things than just transfer across chains. Okay, so that's kind of how the different bridges work, but bridges are really like entry point into like this cross-chain, multi-chain world, and you really need to build some intuition around how to develop applications that fall in this realm. And the biggest thing is like you have to start thinking of Solidity as asynchronous, or like the code in your contracts that you're writing is asynchronous. Right now, if I'm a Uniswap pool, for example, I have that nice curve because all of the trades are ordered because transactions happen synchronously. Like access to the pool is gated by the chain itself. If you were to do this in a cross-chain way, you don't have that same guarantee, and like the constant product is then not constant, so it would be a lot messier. you also have to like take into account that just because the state is something on some source contract, that doesn't mean that at the same time it'll have propagated yet to the target contract. This is like pretty there's also, you know, things about verifying the data that has made it from the source contract. Because you're not doing any like chain native verification, you need to understand whether or not you can trust that response. These are pretty standard patterns in, you know, Web 2 development, but they're pretty new for smart contracts. Sure. Can I? Okay, so yeah, then the rest of the time I'm gonna talk about like building a Zap, and that's a cross-chain application. We're making a new word. And that's not a good thing. But I'm gonna talk about how to do that with Connext. So first off, like, what does that really mean, and what does it look like to kind of create a cross-chain application? You obviously have a sending chain and a receiving chain. We also call these domains, so like origin domains and destination domains, same things. A domain is just an execution environment. You initiate some call on a source contract that you want to do something across chains. That's sent then from your contract to ours, where it's relayed via Nomad, is how the messages are securely relayed across domains. And then it is processed on our domain contract. One cool thing is that you don't necessarily have to wait for Nomad to, like, in a similar way that Hop doesn't necessarily wait for all of the like rollups to clear the bridges. You can just provide liquidity and instead take on the risk that something happens with the optimistic system that you're building on top of. And so like liquidity providers take a fee for that. You also don't have to, and you could just wait for Nomad to propagate the funds. Once they make it to the receiving chain, then it can be processed, and you can actually execute call data on that receiving chain that was specified in the origin chain on some target contract. So we're gonna look at a little bit of one other thing before we get into some example code that's important to understand is this idea of authenticated data. I brought it up before, but kind of how it plays into this system is you have this idea of authenticated and unauthenticated calls. And like, okay, what does that mean? So if you're using an optimistic messaging system, you can only really rely on those messages to be valid once the fraud period has elapsed. Like up until that point, it may be valid, but you can't guarantee it. And so like any data that you're using in advance of that window elapsing is unauthenticated data. But you can also wait for that window to elapse and then treat the data as authenticated. And this is like the source behind our permissioned calls. So like, what is a permission call? A permission call is a call that's opinionated on who the message.sender is. So say I'm an NFT project and I want to like start mints on Polygon, but mint the actual asset on mainnet. Well, then I would need to know who was the original sender of that call on Polygon, and I would have to do that in an authenticated way. Because those transactions would likely just be like passing data between chains. They wouldn't have a lot of value, and so routers would be less incentivized to provide the correct data if it weren't already authenticated. And then, yeah, so the unpermissioned calls where you don't necessarily care about that, anybody can make the call. You can use the fast liquidity and you don't have to wait for the data coming in to be properly authenticated. So when this happens, that means you can make a cross-chain call instantaneously, or like as instantaneous as blockchain gets. And you don't necessarily have to wait for the Nomad fraud timeout. Okay, cool. So now we can dive into a little bit of an example. At a high level, this is just a super, super easy application where you have on your origin chain a source contract that has a function called setVal, and the value that you're setting is on a destination chain. And so you can initiate that whole process in one transaction with Connext. So here is, can you guys all see this? Okay, cool. So here is the source code, and you can see this function update value on chain B. This is the entry point. You can also see, like, so then you create your call params, and these are the call params that you will like call Connext with to initiate this process. You're going to want to specify your call data, and the call data is what you're executing on the destination chain. So in this case, you're setting your value to some specified value. You initiate the transaction, and then on the target chain, once a router picks this up and starts to forward it, the Connext contracts will call update value, which will set the new values on your target contracts, and that just by executing the call data. Another cool thing that you could do but isn't built into this example is you can specify a callback address when you initiate the transaction. And what that callback address is it's a contract on the origin chain that can process return data from the call that was executed on the destination chain. So imagine that instead of this was updating with a given value, it just updates with a random value. So you call set random value on the target, and then on your callback, you would emit a log that showed what the random value on the destination chain was.